Hello everyone. In this video, I will explain the edge classification of depth first search. So this is me, Masud Sohail from North South University. First, let me mention some details about depth first search, which is the full meaning of DFS. So what is DFS? DFS is an algorithm for traversing or searching tree or graph data structures. And the logic of DFS is to go as deep as possible first. So let's explore what are the different edges. There are four types of edges for directed graph. One is tree edge, then forward edge, and the back edge, then the cross edge. So after drawing the tree, we will find some edges which we know as tree edge. If an edge is connected from the parent to its child, then it's forward edge. Reversely, if an edge connects a child to its parent, then it's back edge. And a self-loop is always a back edge. And lastly, while an edge connects a sibling to another sibling vertex, then it's the cross edge, which means it connects vertices in two different DFS tree or two vertices in the same DFS tree, neither of which is the ancestor or descendant of the other. So a DFS graph can be directed or undirected. Depending on the source vertex, the tree structure can be also different. So first we will take the complex case, that is the directed graph. We know no source vertex is initially given in DFS, so let's just pick a source vertex. Let's pick A. So the discovery time for A is 1. It's not finished yet, so finish time is empty. Then we reach B at time 2. Then we reach C at 3. From C we cannot go to anywhere else, so we are done with this vertex. So it will be finished at 4. Then we come back to its parent and there is no other edge going out. So we are done with B also, which is finished at 5. Then we come back to A, but there are some other possibilities which we haven't explored yet. So we can reach the D vertex at time 6. Then there are two edges outgoing. We can take any of them. So we come to F. So here it will be 7, and from here there is no outgoing, so finish time is 8. From D there is another unvisited node, which is E. We will visit that at time 9. And from E there are a few outgoing edges, but all of them are going to visit vertexes, so this will not the part of tree edges. So what will these edges be? Now let's draw a spanning tree from the DFS graph. Once we draw the tree structure, the classifications will be much clearer. So here the root is A, then we are going to B, then we reach at C, then there is no way, so we return to A, and then we come to D, then here is F, so we go back to D, and finally we reach at the last node E. So here all the edges we have used are tree edge. Okay, so this edge which connects the children E to its parent A is a back edge, and this edge connects two vertices and neither of which is the parent or child of the other, so it's not a forward edge, not a back edge, not the part of the tree edge, so it's definitely a cross edge. Now let's continue our DFS. So there is no other possibilities to go from E, so we return from here at time 10. So now there is no outgoing at D, we are finished with it, so we will finish it at time 11. Then we come to A. From A there is another outgoing edge, which is C, that we already visited. For this part, let's just go back to our spanning tree. Here the parent of C is B and the parent of B is A, so C is a descendant of A, so that's not a tree edge, then it's definitely forward edge. And finally there is no other possibilities to go from A, so we here and finished at time 12. So the DFS become pretty and simple after using a spanning tree. Now let's explore the undirected graph. So here we have just two edges. One is free edge and another is back edge, which is like directed part, but there is no forward or cross edge because of the fundamental definition of undirected graph. Now let's see the case of undirected graphs, which is kind of easy than the directed part. So we will start from here. We came this way to reach B, we came to C, and from C there is an edge going to a visited node which is A. It's a non-tree edge which connects a vertex with an ancestor, so it will be marked as back edge. We always will check that if an edge is going to a node which is already visited, then we will mark it as back edge unless that node is its parent. Okay, so from C the edge is going to an unvisited node. Then from E there is an edge which is going to a visited node, so that is back edge. Then we will come to D, and from D there is an edge which is going to a visited node A, so that is back edge. Then we will return to D, and finally we will reach at F. Here we just don't need the pre and post numbers, but we have to keep track of the parent node. See, that's pretty simple. Okay, so this is it. Thanks for your time.